Okay, I guess it's okay. Okay, thank you. So hello everyone, I'm a PhD student at the National Center for Nuclear Research in Warsaw, and today I will present to you my first paper, which was accepted for publication recently with very minor comments, and it will be published very soon. So this paper is about a multi-wavelength study of a supermassive galaxies at the end of their lives around the redshift of 2. So here's the outline of my talk. I will present a very short introduction, then the data that we worked on for this paper, then the results for the ALMA detections and the SED fitting, and the conclusions. So the spectral energy distribution, or SED, is a very powerful tool to derive physical properties of galaxies and help us understand basically the processes that galaxies are undergoing. The UV range, for example, is a direct star formation rate indicator, since the majority of the UV photons are emitted by the young stellar population. Dust, however, will absorb a significant amount of the UV photons and will emit them eventually in the infrared. So therefore, dust is a very important star formation rate indicator. Now let's imagine a galaxy without dust. This is how a completely non-attenuated stellar population would emit. However, if you add dust to it, you can see the dramatic effect that it has on the shape of the SED of a galaxy. Now, to account for dust, we use dust attenuation laws that will allow us to model dust behavior, or what we observe, basically. So there are different attenuation laws. Here I show 3 of them that we used in this paper. We have the Calzetti attenuation law, which is a simple power law and widely used. So, and you have the Charlot and Fall, which differs in its philosophy from Calzetti. It will attenuate the ISM and the birth clouds at a different rate. And we have the Lofaro attenuation law as well, which is a shallower version of Charlot and Fall. So here you see the difference between the 3 attenuation curves. And you can see how Charlot and Fall and Lofaro are shallower than Calzetti at higher wavelength around the near infrared, which will allow a fraction of the older stellar population to be attenuated. So here are the variations in the stellar masses produced using different attenuation laws for a given sample of galaxies. This is just an example to show you the effect. So you can see how flat attenuation laws produce higher stellar masses. This is expected since shallower attenuation laws, such as Lofaro, will assume a more attenuated stellar population at higher wavelength. So how to trace the hydrogen in the cold molecular clouds? Well, hydrogen is the fuel of star formation, So, and its density was found to be tightly correlated with the star formation rate. This is the Koenig-Schmidt law. But unfortunately, we cannot detect the hydrogen, so we rely on tracers such as the CO molecule, which has a low excitation potential, around 5 kelvins. So therefore, it's a very good tracer for the cold interstellar medium, for the star-forming regions, basically. Moreover, the redshift of 2 is when the universe was undergoing its peak of the star formation rate density. So it's, in particular, very interesting to study galaxies around this redshift. So regarding our data, we targeted some of the most massive galaxies at redshift 2 with ALMA in order to better constrain their gas mass and their ISM. But we detected one CO emission line for one supermassive source. It is very massive, as you will see later in the results. It's basically on the tip of the main sequence of star-forming galaxies. So here you see the intensely bright galaxy in the infrared, which has ALMA detection, and it has a bluer galaxy nearby. So we study this system. We detect the CO 322 emission line at 5 sigma confidence and extract the line. We then convert the derived intensity to luminosity, and this luminosity to mass, basically, as it's typically done, to derive the molecular hydrogen using a luminosity ratio, which is R31, to convert the 322 emission to 120, and to convert the CO emission basically to hydrogen mass using the alpha CO. So we use different alpha CO One is 0.8, which is adapted for such galaxies, for ULERGs or submillimeter galaxies. And we use the galactic conversion factor, a Milky Way-like conversion factor of 4.36. And we derive the hydrogen mass. And you will see later in the comparison how it puts this galaxy relative to the other sources. So we investigate the morphology of the CO emission line to closely study the association of the CO component with the other wavelengths. So our source is not visible in the Hubble Space Telescope's observation in the I band, which is the mid-UV rest frame. This is, of course, at redshift 2. Nor it's visible in the CFHT's U band. So this shows you how heavy the dust obscuration is. However, there is a clear offset between the ALMA detection and the near-infrared bands of VISTA and CFHT. So this offset is around 10 times larger than the typical offset found in the Cosmos field. And the VLA detection, however, will at higher wavelength is aligned with the ALMA. So removing a possible systematic error due to the primary beam size. Therefore, this offset is rather physical due to the offset between the cold gas and the stellar population. We investigate the physical properties of our sources using SED fitting with SIGAL. The important part here is that we use a delayed star formation history with a recent burst or quench episode. And we test different attenuation lows, mainly Calzetti, Charlot and Fall, and the shallower Lofaro. And here are the obtained SEDs for our sources. You can immediately see the difference in dust attenuation between the two sources. Here are the obtained results in the table below. So the infrared bright galaxy is in fact a ULERG and even more massive than originally thought due to the Lofaro attenuation low, which will make the mass higher, of course, as we saw. So some of the results in the upper figure, you see the relative position of our source to the main sequence. Here in yellow, you see the blue galaxy, the smaller galaxy. It's a strong starburst. And we compare, of course, our galaxies with sources that have CO detections around redshift of 2 from Genzel and Tacconi. So the blue galaxy is a strong starburst, while the ULERG is a main sequence galaxy using 3 different attenuation lows. Of course, Lofaro provided the best fit for this galaxy. So on the lower figure, you see the gas mass versus the specific star formation rate. For our source, you can see that using a conversion factor of 0.8 underestimates the hydrogen mass of this galaxy. It gives very low hydrogen mass. While using a galactic conversion factor, it places this galaxy among the other galaxies of the comparison sample. And here you see the CO luminosity versus the infrared luminosity. We show the position of our ALMA detected sources using 2 luminosity ratios from Dadi et al. 2015 that are adapted for such sources around this redshift. So using a very low luminosity ratio results basically in a starburst, which, in a main sequence. So using a typical luminosity ratio gives us a starburst, which contradicts the SIGAL results. And you see that using a typical luminosity, so it's very contradicting. And took the conclusions, a galactic conversion factor when used along with the least excitation ratio from Dadi et al. 2015 confirmed the relative position of our ULERG to the main sequence, so which was confirmed by the SED result. The depletion time of our ULERG is of the order of 100 mega years, which is larger than what is expected in typical main sequence galaxies, which suggests that this is a galaxy that is caught in the middle of quenching following an earlier starburst activity. So basically, it's a starburst galaxy on the main sequence, and such galaxies were also studied in the literature recently, such as Elbaz et al. 2018 for starburst on the main sequence. So thank you for your attention.
Thank you very much.
Hello?
Okay.
Okay.
Yeah, I don't see any question. So any question? Okay, I start your question. My question. So I think we also have a dust. Can estimate dust mass or something. Is it useful?
I'm sorry, I didn't hear. You see what?
So maybe you may have dust mass also. So
The dust mass, yes, it's derived as well.
could it be useful to constrain some dust mass, or I don't know.
What was the question exactly? Sorry, I cannot hear clearly.
So could the dust mass useful to constrain that gas mass?
In fact, yes, the dust mass was useful basically to constrain, basically to judge the placement of this galaxy on the dust evolution relative to the stellar mass evolution of basically the dust to stellar mass ratio, and this galaxy is, yes, it's among so as expected, yes, it's not very different than other galaxies around this region.
Thank you. Any other question? We still have, I think we still have time. Yeah. So local participant, or maybe raise your hand. Yeah.
I have one question about the redshift. How did you decide the redshift of this target?
How did I decide what? I'm sorry.
Redshift. Spec Z or photo Z or how did
so the redshift, yes. So this galaxy originally was from the Cosmos catalog. So we knew the photometric redshift, and it had a spectroscopic redshift and the Z Cosmos catalog as well. Let me just find it. So yeah, from Lake et al. 2016, and it had a spectroscopic redshift from the Z Cosmos catalog, as I said. But we also check the redshift, which is from the CO emission line. Here the contours in green, and it confirms the photometric redshift. It's 2.15 basically.
Okay, thank you very much.
Is there offset between spec Z and then CO redshift?
Between the spec Z and the redshift.
There's an offset between stellar population and gas, right?
And the gas, yes, exactly, because this is the rest frame. So, yeah.
So there's an offset in redshift as well?
At redshift of 2. So this is, so basically what you see here is the near infrared, okay, 2.14. But in rest frame, it will be around redshift of 2. It will be around the optical range, so the stellar population.
I'm asking redshift, there's offset between spec Z and then CO redshift.
Okay. Okay, sorry. Now I understood. There is a small redshift, but to be honest, they agree. It's 0.01 different redshift. So yeah. And however, something interesting here. Thank you for raising this issue. The spec Z from the Z Cosmos was derived for both of the sources, for 2 sources basically, for these, because it was not blended. But using the ALMA detection, we confirmed as well the redshift of this galaxy. And this galaxy has a photometric redshift.
So maybe it's because of this blue galaxy's offset.
Maybe, yes, it could be.
Any other question? Okay. Okay. If not, let's thank the speaker again.